we consider two-dimensional satellites which is in orbit around the Earth, and the state equation for the satellites are given here. So in this satellite there is an inertial wheel which allow us to orientate the satellite, and in this exercise we want the satellites look toward the center of the Earth. The expression for the gravity is given here, where P is the position for the satellite. So it is a two-dimensional satellite. I will represent here. So I represent like this, and here the satellite is able to see forward, but I want to be directed to the center of the Earth. So the position of the satellite is given by a vector which is P1 and P2. So it is a two-dimensional vector, and the heading for the satellite is given by R. So I will represent by an angle like this, but R corresponds to the rotation matrix 2, 2, cos psi minus sine psi, sine psi, and cos psi. So this corresponds to the evolution of the satellite. What about this quantity? So omega corresponds to the rotation rate for the satellite, so it belongs to R. But this quantity is a matrix which is given a skew-symmetric matrix 0, 0, minus omega and omega. So it is a 2, 2 matrix, and I can multiply by R, which is a 2, 2 matrix, and I will obtain the derivative for R. The quantity τ corresponds to the torque, and we are able to, inside the satellite, I represent like this in a big format, and inside this one there is some kind of wheel. So the wheel I will represent by the cross like this, and when I have a torque between the satellite and the wheel, which can turn like this torque, then there is a counter reaction which makes the wheel turn in one direction and the satellite in the opposite direction. So τ is a quantity which belongs to R. This is the Euler equation, which corresponds to the Newton equation, but for the rotation. RW is the orientation of the wheel, which is inside the satellite. This one corresponds to the rotation rate of the inertial wheel. And due to the action-reaction, we understand that here, if we have τ, here we have minus τ. I have to simulate the system, and first I will need to draw it. So to draw it, I propose the following Python program. Where here I draw the disk corresponding to the Earth. Here I draw some kind of robot which has the shape of a triangle, and here I draw the inertial wheel. So when I write here the log, I mean that from the rotation matrix R or RW, I extract the corresponding angle. So to draw it, I will first initialize the position for my robot, the two rotation matrices for the wheel and for the satellite to identity, here the speed of the satellite inside its own frame. So here VR is the speed of the satellite, but the expression is given in its own frame, so it should be like this. It has to be tangent to the trajectory represented here. Here for the initialization, I will take for the rotation speed for the wheel and also for the satellite equal to 0. I draw the satellite given by this function. So this is my program. I run it, and I see here the satellite, which looks like a Dubbin's car, and here the cross in red corresponds to my inertial wheel. The gravity J is oriented towards the Earth, like this, and is taken as given by the Newton law by minus P, the position for the robot, divided by the norm of P power 3. So this is this quantity. Now for the simulation, I will isolate inside a single vector x the position P, VR the speed in the satellite frame, omega the rotation rate for the satellite, and omega wheel for the inertial wheel. So inside a single vector, and for the integration I will use a Runge-Kutta method, since x belongs to Rn. There is no need to use a specific exponential integration method. But now, for this one and this one, since it is a rotation matrix, it belongs to a Lie group, and I want to avoid singularities using angles. So for this, I will use the exponential integration, which tells me that r at time t plus dt is equal r of t, something approximation of course, multiplied by the exponential of dt omega of t. So this is a multiplication, and this corresponds to a rotation, a 2-2 rotation matrix. Take care, this one belongs to R, but the exponential gives me a 2-2 matrix. And the same manner for the wheel, I will have R wheel at time t plus dt is equal orientation for the wheel, R of t, which is a rotation matrix, multiplied by exponential dt rotation rate for the wheel of t. So I will do this, and for this I will use the following Python program. So this corresponds to a Runge-Kutta method, RK, Runge-Kutta. So it is a specific midpoint Runge-Kutta method, which is quite short, so easy for in this case. And it will provide me x at time t plus dt, from x at time t. Okay, so Runge-Kutta method. So for the function f, which depends on x and tau, the input for my system, I will take from x, isolate p, vr, w, wr here. Okay, so this is this one correspond to this. The gravity has been given previously, and this one correspond to that, and so on. So I will stack all them, and in fact it will return me x dot, an expression for x dot. Then from f and x I will use the Runge-Kutta method to provide me x, an estimation for x at time t plus dt. Okay, I reshape in order to isolate from x P, VR, W, W, W. Okay. And here it is exponential integration method for the rotation matrices. So all this one corresponds to my integration scheme. I write the simulation loop here, which calls me my integration scheme here, and I draw the satellite at each iteration. I run this, but you will observe that tau equal to 0, that it means that there is no control. Run. And I can see here my satellites turning around the Earth, but without any control for the orientation. This is why the orientation remains constant, and it is also the case for the inertial wheel. Second and last question, I have to find a controller so that the satellite is always looking toward the center of the Earth. Okay. This is the state equation for my satellite and the inertial wheel, and the input is tau, the torque. And from this I want to build a controller so that this one is always oriented toward the Earth. So I will build some kind of desired orientation, and I put like this. So if the satellite which has this orientation at this moment, X and Y, if it has so front and up, if we want, if it has this orientation, the magenta orientation, then it will look toward the Earth. So this one I will call it RD, like desired. Okay. So for my controller, I will have to add here as an input the desired orientation, like this. Okay, so for this I will build the unit vector. I will call it n, and n corresponds to minus p, the position, divided by the norm of p, so that it is a unit vector, like this, oriented to the center of the Earth. From this I will n1, n2, I will be able to build RD, which is equal to n1, n2, and to make a rotation matrix I will add another vector which has minus n2 and here n1, okay, which depends of p. Now from this I will build the error between my orientation and RD. I will use the logarithm for this, so I take the logarithm of the desired orientation RD multiplied by R transpose. So recall that I cannot make the division between in the rotation matrices between the desired and the actual rotation, because it is I cannot add rotation matrices. I can only multiply them. It is a Lie group. That's why this is why I have to take the logarithm to have the error. So this is why here I will put I equal log of RD multiplied by R transpose. R transpose is obtained from here. Okay. In the same manner, I will have, if I want to use a derivative term, so not only proportional, I need also the derivative for the error. And for this, it will be given by the desired rotation rate. So the actual rotation rate is omega for the satellite, but I want omega to be equal to omega d. So it will correspond to the rotation rate of the magenta of frame of RD. So it will be given by P1 V2 minus P2 V1 divided by the norm of P square. So I put it once I have here, I will be able to compute the torque. So here, given by this formula. And for the torque, I will take a proportional and derivative control, which tells me that tau equal to a coefficient K1 1 E minus K2 multiplied by omega minus omega t. Okay. So now I will implement this. For the implementation, I will use the following Python program. Where I can see here my vector n computed here, RD the desired rotation matrix, here 0, which is an element of R. This one is a 2-2 matrix, this one a 2-2 matrix, but the logarithm gives me an element of R. Then from this, I have to express VR in the frame of the Earth to get V, to be able to compute WD. Okay, which was given here. Okay, I switch to Python. This is my program where the torque is obtained by the controller. I run it, and I can see it takes quite a long time to point toward the Earth. This is why I have to change my gain. So here I will put it something larger, for instance 10 or 100. I run it. Whoop. I can see that it oscillates. This is why I have to increase the derivative term. I will start with 10, like this. I can see that it is better, but there is some kind of delay. I can see also the wheel turning as a reaction to the motion of the satellite. So to avoid the delay, I will have to increase my gain. I will put something like 300. And I can see that the satellite always points toward the Earth.